Hello and welcome to Group 3's final project presentation for the Mechatronics course at Carleton University. Members of the team include Matthew Betts, James Alexander, Zachary Riley, and Jeremy Levasseur. The purpose of this project was to design and analyze a mechatronics system that incorporates all of the typical mechatronic components that you would find in real-world applications. The team decided to investigate a simpler take on the Stewart platform. This system has 6 prismatic actuators attached to the base of a platform, allowing it to move in 6 degrees of freedom. General purposes for Stewart platforms include flight simulation and helicopter landing pads. The model that was designed by the team involves only 2 degrees of freedom and can be seen in the figure on the left, which was created in Fusion 360. There is one static link in the center with 2 dynamic links on the sides to rotate the platform as necessary. The goal of the system, for the purpose of testing, was to balance a ping pong ball in the center of the platform. To simulate the system, multiple programs were used. This includes Simulink, OpenCV, and Python. Each of these will be discussed in the video. Initially, we began modeling the system with Simulink due to its toolbox dedicated specifically to the simulation of physical models and their control systems. This toolbox is called Simscape Multibody. The simulation we created using this toolbox only includes the platform and the ball, not the servos or linkages. We knew that the microcontroller that we would use for this mechatronic system would be a Raspberry Pi that uses the programming language Python to control the various components. At the same time, this mechatronic system requires a camera to locate the ball while viewing the platform from overhead. Since we wanted to integrate the servo motors, linkages, platform, ball, and camera all into the same simulation, we realized that we would not be able to use Simulink and instead would have to model the entire system using Python. This required us to create a custom simulation using the third-party graphical user interface library, tkinter. We created the physics of this simulation from scratch using Newton's laws of motion. We needed to predict where the ball would end up depending on the platform's orientation, and then update the graphical user interface to reflect these changes. Throughout the simulation, the properties of the ball and platform are being kept up to date using kinematic and dynamic equations. One of the assumptions made for this simulation was that no slipping occurs at the point of contact between the ball and the platform. All the code for this simulation can be seen in our project GitHub repository, which is linked in the description of this video. When the simulation file is run, 4 windows pop up. The main window is a bird's eye view of the platform where the ball is represented by a red circle. 2 additional windows are generated that show the motion of the servo arms, linkages, and platform viewed from either side of the system. As the ball moves around, the servos react by rotating their arms, causing the platform to tilt in the X and Y planes. If this mechatronic system were to be made into a real-world application, an overhead camera would need to constantly track the ball and return its X and Y position. Fortunately, there is a Python library called OpenCV that makes it easy to analyze a video feed frame by frame and locate an object based on its color and contour. Integrating OpenCV with the simulation allows for the ball's location on the platform to be returned easily. The result of our work is a simulation that can react to forces applied in any direction, returning the ball to the center of the platform. And with that concludes our presentation. Thank you for listening.